Today we are testing the LD2410D 24 GHz radar sensor with XIAO ESP32C3 to see what this tiny sensor is really capable of. Can it accurately detect the distance of my hand, sense slow and fast movements, and continue working in complete darkness? Let's find out. To start, I will move my hand toward the sensor while monitoring the distance reading in real time. As you can see, the measured distance changes as my hand gets closer or further away. After this initial distance test, we will check how well it detects slow movements. Compare that with faster movement, and finally put it to ultimate test by operating it in complete darkness to see if lighting conditions have any effect on its performance. So let's get started. We will require the following components for this project: XIAO ESP32C3, LD2410D radar sensor, buzzer module, SSD1306 OLED display, breadboard, and some jumper wires. Before we jump into the experiment, let's understand what makes the LD2410D such an interesting sensor. The LD2410D is a 24 GHz mmWave radar sensor developed for human presence, motion detection, and distance measurement. Instead of relying on heat like a PIR sensor or visible light like a camera, it continuously transmits low power 24 GHz electromagnetic waves and analyzes the reflected signal using the Doppler effect and signal processing algorithms. This enables the sensor to detect a person's presence, movement, and approximate distance with higher accuracy. One of the biggest advantages of the LD2410D is its ability to detect both moving and stationary people, while most PIR sensors only trigger when someone is moving. The LD2410D can continue detecting a person even when they are sitting or standing almost still by sensing tiny body movement such as breathing or slight posture changes. This makes it an excellent choice for smart homes, automatic lighting system, occupancy detection, security system, office automation, and other IoT applications where reliable human presence detection is required. The sensor divides its detection area in multiple configurable distance gates, allowing you to adjust the sensitivity for different ranges and reduce false detection. It communicates with the microcontroller such as the XIAO ESP32C3 through a simple UART interface, making integration straightforward. Using the official configuration tool. Parameters such as detection range, gate sensitivity, and motion threshold can be customized to suit different environments. Another important advantage of the LD2410D is that it performs consistently regardless of lighting condition. Since it uses millimeter wave radar instead of visible or infrared light, it works equally well in bright daylight, dimly lit light, and complete darkness. It can also detect targets through certain non-metallic materials such as plastic, glass, and thin wooden panels, allowing it to be hidden inside enclosures for a cleaner product design. Now let's connect the LD2410D sensor with XIAO ESP32C3. Connect the VCC pin of the LD2410D radar sensor with V-bus pin of the XIAO ESP32C3. Ground pin with ground. Connect the TX pin of the LD2410D radar sensor with GPIO pin 20 and RX pin with GPIO pin 21. Connect the VCC pin of the SSD1306 OLED display with V-bus pin of the XIAO ESP32C3. Ground pin with ground. Connect the SDA pin with GPIO pin 6 and SCL pin with GPIO pin 7. Now let's take a quick look at the code running on the XIAO ESP32C3. First, I include the required library for communication with the OLED display and rendering text on the screen. Then I define the display resolution and initialize the LED using the I2C interface. Next, I specify the UART pins connected to the LD2410D radar sensor, with one pin used to receive data from the sensor and other to transmit data if needed. In the setup function, the serial monitor and hardware UART are both initialized at 115200 baud, which matches the default communication speed of the LD2410D. The LED display is also initialized, and startup message LD2410D ready is shown to indicate that the system is ready to receive data. Inside the loop function, the ESP32 continuously listens for data coming from the radar sensor. Whenever a complete line of data is received, it is printed to the serial monitor for debugging. The program then scans the received text and extracts only the numeric characters which represent the detected target distance. Finally, the LED display is updated based on the received data. If a valid distance value is found, the display shows target detected, along with the measured distance in centimeters. If no numeric value is present, the program assumes that no target has been detected and displays no target. This simple approach allows us to monitor the radar sensor detection status and measure distance in real time on both the serial monitor and the LED display. Now it's time for the first practical test. As you can see, there is nothing in front of the radar sensor, so the LED display shows no target, indicating that no object has been detected. Now I will place my hand in front of the sensor. As soon as the LD2410D detects my hand, the display changes to target detected and show the distance of the target from the sensor in the centimeters. One thing I noticed during testing is that the sensor does not just detect my hand when it's directly in front of it. I tested it from several different angles and it was still able to detect my hand and report the distance, demonstrating that the LD2410D provides a fairly wide detection coverage rather than requiring perfect alignment with the sensor. Now let's set up it for motion detection. Connect the VCC pin of the LD2410D radar sensor with V bus pin of the XIAO ESP32C3. Ground pin with ground. Connect the TX pin of the LD2410D radar sensor with GPIO pin 20 and RX pin with GPIO pin 21. Connect the out pin of the LD2410D radar sensor with GPIO pin 3 of the XIAO ESP32C3. Connect the VCC pin of the buzzer module with VBus, which is 5V pin. Ground pin with ground. Connect the signal pin with GPIO pin 10. This program is designed specifically for testing the LD2410D radar sensor. It first establishes UART communication with the sensor and configure important parameters such as the maximum detection range and the sensitivity of each distant gate for both moving and stationary targets. These settings help optimize the sensor performance while reducing false detection. After configuration is complete, the ESP32 continuously monitors the sensor presence output pin. Whenever a target is detected, an LED turns on and the program prints a detected message along with a timestamp to the serial monitor. When the target is no longer detected, the buzzer turns off and the program reports how long the target remained in view. To keep the serial output clean and easy to understand, messages are printed only when the detection state changes, making it ideal for recording and analyzing the different tests. Now let's move on the practical demonstration. I have powered on the XIAO ESP32C3 and as you can see, there is currently no movement in front of the radar sensor, so the buzzer remains off. Now as I move in front of the LD2410D, the sensor detects my movement and the buzzer immediately turns on. When I move away and there is no longer any movement or presence being detected, the buzzer turns off again. This simple test shows how the LD2410D can be used to detect human movement and control an output device, such as a buzzer in real time. Now let's test the sensor with faster movement. This time I am moving quickly in front of the LD2410D to see if the increased speed affects its ability to detect me. As you can see, even this faster movement, the sensor continues to detect me and the buzzer turns on. This confirms that the LD2410D can reliably detect both slower and faster movement during our test. Now let's take the test one step further. I have turned off the lights, making the route completely dark, and I will move in front of the LD2410D. As you can see, the sensor still detects my movement and the buzzer turns on. This is one of the major advantages of radar-based detection. The sensor does not depend on visible light, so it can continue detecting movement, even in complete darkness. This makes the LD2410D useful for application where reliable detection is required both day and night. And that brings us to the end of our LD2410D radar sensor testing. In this video, we connected the sensor with the XIAO ESP32C3 and tested its ability to detect target from different angles, measure distance, detect both slow and fast movement, and even work in complete darkness. As we saw, the sensor continued to detect my reliability under all of these conditions. If you found this project helpful, don't forget to like the video, subscribe to the channel and turn on the notification bell for more Arduino, ESP32 and sensor based project. Thanks for watching and I will see you in the next video.